Good day everyone, I am Jamaica Teleteguit and today I will present on permutations and symmetric groups, which are a fundamental concepts in abstract algebra, and we will discuss their definitions, examples, formulas, and prove that symmetric groups satisfy all four group actions. But before I dig deeper to our main discussion, please allow me to introduce our objectives first. So at the end of this discussion, at least 90% of the students will be able to first, define permutation and symmetric groups using appropriate mathematical terms. Second is to appreciate the application of permutations in symmetric groups in real-world situations. And lastly, to represent permutations and symmetric groups in real-world context using diagrams, symbols, or physical arrangements. Permutation and symmetric groups are important concepts in abstract algebra. They help us understand rearrangements and symmetry in mathematics. So groups are mathematical structures that help us understand patterns and operations. So among this, permutations groups and symmetric groups are particularly important because they describe all possible rearrangements of a set. They are not only abstract concepts but also have real-life applications in things like arranging students in line, scheduling tasks, and even in cryptography. So now, what is permutation? So a permutation is a bijective function from a set to itself. It rearranges the elements of a set without repetition. So when we say bijective, it is a combination of injective and subjective, which means no repetition and no one is left behind. So example of it is for element 1, 2, 3, a permutation is 2, 1, and 3. So a permutation is simply a way to rearrange the elements of a set. For instance, if we have element 1, 2, 3, the original order is 1, 2, 3, and a permutation could rearrange it to 2, 1, 3 or 3, 2, 1 or etc. So in formal mathematics, a permutation is a bijective function, which means every element maps to a unique without repeating or missing any element. So always remember that permutation simply means without repeating or missing any element. Now let's proceed to the permutation notation, which first is the two-line notation. So permutations can be written in different ways. The two-line notations show the original elements on top and their images after permutation on the bottom. So the cycle notation is more compact. 1, 3, 2 means 1 goes to 3, 3 goes to 2, and 2 goes back to 1. So cycle notation is very useful when studying groups because it clearly shows how elements are rotated. Now let's proceed to the permutation group. So a permutation group is a group whose elements are Now let's proceed to the permutation group. So a permutation group is a group whose elements are permutations of a set and whose operation is function composition. It is a subgroup of some symmetric groups or some S sub n. So a permutation group is a set of permutations that satisfy the group rules. Closure, the group rules are closure, associativity, identity, and inverse. So under composition. That means if you apply one permutation after another, the result is still in the set. So permutation groups can be subgroups of a symmetric group. So they are useful because they model rearrangements in a structured mathematical way. Now, what is symmetric group? So the symmetric group or S sub n is the group of all permutations of n elements. It is the largest permutation group on n elements. So the symmetric group or S sub n includes every possible permutation of n elements. For example, S sub 3 has 6 elements, which include always to rearrange 1, 2, 3. So symmetric groups are important because they are all the complete permutation groups, meaning they contain all possible rearrangements. They form the basis for studying a permutations in abstract algebra. So example of it is S sub 3, the element of E, 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. So for the S sub 3, the set has 3 elements. Its 6 permutations include E is the identity or leaving everything in place. The 1, 2, 1, 3, or 2, 3 swaps of 2 elements. 1, 2, 3, 1, 3, 2 rotations of all 3 elements. So these examples show how all possible arrangements are accounted for in the symmetric group. And now, let's proceed to the order of symmetric group. The number of elements in S sub n is given by, so this is the formula of symmetric group. So the order of a symmetric group, that is, the number of elements it contains, is given by n factorial. So this formula comes from counting the number of ways we can arrange n distinct elements. So each position has fewer choices as we fill it, which is why we multiply descending numbers. Like, for instance, we're going to find the element of S sub 5. So 5 times 4 times 3 times 2 up to 1. So we are going to solve it in descending order or descending numbers. So again, as what I've said earlier, that for instance, we're going to solve for the elements of S sub 5. So S sub 5 equals 5 times 4 times 3 times 2 times 1 equals 120. So for S sub 5, we have 5 elements. Using the formula, 5 equals factorial of 5 is 120. So we know there are 120 possible permutations, and we can even construct them systematically by fixing the first element and permuting the remaining 4. So this shows both a formula and a logical way to count permutations. Now let's proceed to the group axiom. So a set G with operation is a group if it satisfies closure, associativity, identity, and inverse. So to be a group, a set must satisfy these 4 key properties. So these axioms ensure that the set behaves in a structured way under its operation. Symmetric groups satisfy all 4 axioms, which makes them one of the most important examples of groups in mathematics. Is closure. So, example here. For all sigma and tau in S sub n, the composition of sigma and tau is also in S sub n. For example, the permutation 1, 2 composed with 2, 3 equals 1, 2, 3, 1, 2, 3, which is in S3. So, closure means that combining 2 permutations in the group always results in another permutation from the same group. For example, composing 1, 2, and 2, 3 gives 1, 2, 3, which is also in S sub 3. So, S sub 3 is closed under composition. Now, let's proceed to the second property, which is the associativity. So, the sigma composed with tau composed with rho equals sigma composed with the composition of tau and rho. So, associativity means the way we group the operations does not affect the final result. Permutation composition is function composition, which is always associative. So this is a fundamental property that all systematic groups automatically satisfy. And now, the third property is what we call identity. There exists an identity element E in S sub n such that sigma composed with E equals E composed with sigma equals sigma. So for example, the identity permutation E is 1. 2, 3, which leaves everything in place. So the identity element leaves everything unchanged. For S sub 3, the identity permutation is E, 1, 2, 3. So applying E before or after permutation does not change the permutations. Last property is what we call inverse property. So, for each sigma in S sub n, there exists an inverse of sigma such that sigma composed with its inverse equals the identity. For example, the inverse of 1, 2, 3 is 1, 3, 2. So, every permutation has an inverse that undoes its effect. For instance, 1, 2, 3 rotates elements forward, so 1, 3, 2 rotates them back. So, composing them gives the identity permutation E. So, this satisfies the inverse action. Since S sub n satisfies closure, associativity, identity, and inverse, it follows that S sub n is a group under composition. So, by checking all 4 actions, closure, associativity, identity, and inverse, so we confirm that symmetric groups are indeed groups. So, this is why they are called permutation groups that form a formal structure in abstract algebra. Now, let's proceed to its real-life interpretation. So permutations model real-life processes such as seating in arrangements, scheduling, cryptography, and symmetry in physics. So symmetric groups are not just theoretical. They model how we can rearrange objects or tasks in real life. For example, arranging students in different seating orders, scheduling meetings, or analyzing symmetry patterns in molecules in chemistry. So these applications show the importance of permutations in symmetric groups beyond mathematics. So permutation and symmetric groups provide a formal way to study rearrangements and symmetry. So they are central objects in abstract algebra and appear in many areas of mathematics and science. So in summary, permutations show how to rearrange elements. Permutation groups structure these rearrangements into a group, and symmetric groups include all possible arrangements. So by verifying in the four group actions, we see that symmetric groups are proper groups. So they have wide applications in mathematics, science, and even in real-life situations. So understanding them is fundamental for anyone, especially those who are studying abstract algebra. And those are my reports. I hope that you've learned something from my topics. Thank you.